Hi, my name is Eileen Figueroa, and I have been working with James and Michelle, along with our advisors Dr. Neil Zoltani and Laura Munoz, on electrical circuit modeling of rhythm disorders in the heart. When electrical impulses, or action potentials, move across cells in the heart beats. Electrical alternance is the alternating patterns of action potentials, or electrical waves, inside the heart. This pattern, as shown below on our figure under concordant alternance, is long, short, long, short. A phenomenon known as discordant alternance is when these patterns are out of phase in different regions from the heart. The pattern ends up shifting from long, short to short, long, short, long. Ventricular fibrillation, as shown at the end of our figure, is a cardiac rhythm disorder that is a leading cause of death in the United States. When VF occurs, the heart stops pumping and the ventricles begin to quiver, leading to cardiac arrest. Computer simulations, along with circuit theory, are used to model the heart's wave propagation. This allows for simplified calculations and manipulations in the model. However, the simplicity can create inaccuracy within these models. Resistors are used to model intercellular connections. Voltages and currents are used for the electrical state of the model. Capacitors are used to model the cell membrane, and nonlinear elements represent the ion channels. Discordant alternance can be modeled by current gap junction-based models, like the one below, but only if the size of the heart in this model is far larger than reality. In other words, our problem here is that the patterns that are out of sync wouldn't fit in our normal-sized heart. A theory behind why this may be ineffective is that we are oversimplifying the model of electrical connectivity between cells. Our idea is to use an effective model with cell coupling to simulate the discordant alternance instead of the gap junction model. Effective connections are an augmented form of communication between cells. It is composed of resistors, capacitors, and nonlinear elements, such as sodium ion channels. Resistors and capacitors were added to enable a decrease in the size of the heart for our model. An example we have below is based on Kuchera's effective model. And so in the green dashed circle is the effective model, and the blue box is the added resistors and capacitors, and in the orange box is the original resistor from the gap junction model. The gray boxes in the background represent our cells. We are utilizing electrical circuit models to duplicate the heart cells because the wave impulses that travel throughout the heart are like the way current passes through a circuit. Capacitors have some effects on waves such as action potentials, which include allowing wavefronts to pass through easily due to the high frequency. Theoretically, they act as barriers to wavebacks due to the low frequency, causing the waveback more trouble to pass through. This should allow the action potentials to be different sizes, making them closer together, which can help us better understand discordant alternance. Furthermore, being able to understand the circuits will lead us to a more in-depth analysis of these models. The discordant alternance scale size is affected by the wave propagation speed. Therefore, we will study the wave propagation speed using a 100-cell fiber model based on Kuchera's effective network. We will focus attention on two equivalent circuits, which represent, respectively, one of the cells in the 100-cell model and the spacing between two such cells. These equivalent circuits are simplified versions of segments of the 100-cell fiber model, which was accomplished by removing some components and checking whether the circuit behaves similarly to the original circuits. The purpose behind these circuits is to aid in our understanding on what causes the delay between the ion channels, which are boxed in the red on our figures below, firing in the circuit. The time delays determine the wave velocity. So above we have our 100-cell fiber model, and these are cells 50 and 51 that we chose to study, represented here in this model. As you can see, equivalent circuit 1 will be representing the space between these cells, which is known as the cleft region, and equivalent circuit 2 will be representing the travel from one end of the cell to the next. This is one of two equivalent circuits that was created once we identified the branches of the circuit where most of the current was traveling. We used the MATLAB simulation to be able to create equivalent circuit 1. The goal behind this equivalent circuit is to understand the time delay that occurs when the action potentials travel across the cleft region, as shown on our figure on the right. This is cell 50, This is the cleft region, the space in between the cells, and then this is cell 51. We have two figures here. On the figure to the left, we have a comparison between the equivalent circuit and our 100-cell model. The dashed lines represent the equivalent circuit, sorry about that, and the solid lines represents the 100-cell model. Between 0 to about 16 milliseconds, as shown here, it is constant because it takes 16 milliseconds for the action potential to arrive at cell 50, node 3, the first of two cells of interest. Once it does hit 60 milliseconds, the current passes through node 3, flowing through the ion channel, which produces a sudden increase, as seen in our figure on the left. While traveling through the cleft region, you see a negative dip at node 4, represented by the red, which reaches negative 38 millivolts. When the current reaches the following ion channel in the next cell, 51, it charges CCl, which rapidly increases like the increase in node 3, as seen in the figure on the left. Now, with working with resistor capacitors, or RC, we have to calculate a time constant. And so we wanted to see how fast the CCl, which is boxed in the red, charge. And so we used Kirchhoff's current law, KCL, on node 2, which is where the green circle is. And we ended up finding out that our tau is 2 times CCL times R, which we believed is less than our threshold of 0.2 milliseconds, which we were able to prove once we calculated a value of 0.004 milliseconds, which overall tells us that the capacitor CCL can keep up with the charge in V1T in our figure. This is the second of two equivalent circuits that was created once we identified the branches of the circuit when most of the current was traveling. We used a MATLAB simulation to create equivalent circuit number 2 as well. The goal behind this circuit is to understand the time delay that occurs when the actual potentials travel from one end of the cell to the next, hence why using cell 51. Once again, you see the figure on the left representing the waves traveling. The dashed line is the equivalent circuit, the solid line is the 100-cell model. On the right, you see the representation of the nodes along with cell 51. Between 0 to about 16 milliseconds, where it's constant, it takes 60 milliseconds for the actual potential to arrive at cell 51, hence why the lines are constant. Once it hits 60 milliseconds, the current that is passing through from the ion channel passes through node 5, here, charging CCl, hence the rapid increase, as seen in the graph, where red is V5. The negative dip occurring at node 4 and 6, where it's the yellow and the blue, is given based on equivalent circuit 1, as seen previously. At node 4, the negative dip reaches negative 36 millivolts. The RC time constant for equivalent circuit 2. So in order to have a better understanding of the ion channel, we solve for its Thevenin equivalent, a theory in which, if correctly derived, should leave us with a voltage source of E Thevenin in series of a resistor R Thevenin and still behave the same as its original state. In this case, our R Thevenin is R int, or internal resistor. This resistor is much larger than RR, which means that Cm dominates the RC time constant of this circuit. In other words, our formula for tau is equal to internal resistor R int times C sub m. Our time constant tau is 0.25 milliseconds as shown in the black region below. To summarize our research, our goal was to understand what determines the electrical wave velocity in a cardiac fiber with effective network coupling. We built a computer model of a cardiac fiber, constructed equivalent circuits of two key portions of the fiber, and conducted a detailed analysis of the wave transit times through the equivalent circuits. These time delays were used to reconstruct the wave velocities, which compared favorably with existing theory and direct measurements of velocities in the cardiac fiber computer model. Our new understanding of what determines the wave velocity will allow us to use an existing theory by Echevarria and Karma to explain how our effective network decreases the scale length of discordant alternance to a size that will allow it to fit into the heart. I would like to take the time to acknowledge our advisors, Dr. Neil Zoltani and Dr. Laura Munoz, my RAU/Alzheimer's group, Michelle and James, the School of Mathematical Sciences at RIT, and of course, LSAM, Kate Torrey and Giovanna Victor. Thank you very much. Now I am opening the floor to any questions. Thank you for listening to my presentation.